Alrighty, guys. Can you hear me again? Good. Alrighty. So next up is this proof, and you have to bear with me a little bit. It's going to take a few pages to get through. Each step is not terribly complicated, but there's quite some. It's not straightforward. This is one of the longer proofs that's in this course. So let's try to get through it so we can see where all the pieces come from. All right, so proof. The right, so we need to prove. We need to establish this f of x being like 1/2 minus 1 over pi, and then that integral from 0 to infinity of, and then you have the imaginary component e to the minus I tx, characteristic function phi, everything divided by t, dt, and this is for x and r. Right, so we're claiming, so here we're claiming, so we need two things. So we need two properties. So one, we're claiming that this limit, that this is an improper integral. Right? So we're claiming here that the limit as n goes to infinity of the integral from 0 to n, this imaginary component of e to the minus I tx, I t, t dt. We claim that this thing here, that limit, it exists. You'd also wonder about it around 0, but around 0 it's not bad because it's going to be a 0 over 0 situation, just like sine x over x for x equal to 0. The problem is up here at plus infinity. This is where the improperness comes from. So we need to prove that this exists, and two, we need to prove that this limit, we need to prove that the limit, it equals something very specific, like that this limit here equals f of x minus 1/2 times minus pi. Right, we need to compute what this limit here is and prove that it's equal to this. Okay, so to do so, what do we need? We're going to start by rewriting this imaginary component up here. So let's just recall it. If I have a complex number, so if I have my z here in the middle, z is equal to a plus ib. So here we have, this is the real part. This here is my a, and over here we have b. If I look at the conjugate, then I swap down to, so my conjugate c bar, this is equal to a minus ib. This is the conjugate. So if I look at the imaginary component of c, right? So this here is a real number. The imaginary component of z, how can I write it? I can write this as can write this as what? If I take the difference, c minus c bar, this will be 2IB. And I just want to get B, so if I divide by 2I, this should give me a B. And likewise, if I want to look at the real number, this is again going to be the real part of the complex number Z. This is going to be a real number. And the way I can get that one is if I just add them up. That'll give me 2A, so I need to divide by 2. This is going to give me A. So there are different ways that I can express this imaginary part up here. There are different ways for me to write this, and let me write them out. So on one hand, I can write. So on one hand, I can write imaginary part of e to the minus I t x 5t divided by t. How would I be able to write it? Well, I'll use the formula for the imaginary part that we had down here. This will be equal to, downstairs I'll have 2it. Upstairs I'll have the number e to the minus itx 5t minus its conjugate e to the minus itx 5t, and then the conjugate of this thing. Okay, so how do we do the conjugate? So maybe we should just recall the things computing the conjugate of. So conjugate of a product is equal to the product of the conjugates. Okay, so this EITX, what is that? TX, this is my angle. So if I have a number here, this is my Z, this is my number theta. But if I want to do the conjugate, I just go down with minus theta. Excuse me. And so that's going to take care of the first one. I'll just eliminate the negative sign. Right, instead of going up, I go down. What about 5t? 5t is this integral EITX f of x dx. So if I do the conjugate, and I just move the conjugate inside, f is real, so there's no conjugation here. The conjugation is going to come from minus itx f of x dx, and then that will be phi of minus t. Right, instead of having a t, I will have a minus t here. So that will allow me to re-express that mess we have up here as e to the minus itx 5t minus, and then the first, like the conjugate of a product, I have to do the product of the conjugates. This will be itx and then phi of minus t, everything divided by 2it. So that would be one way to express, what we have in here. I can use it, I can write it like this. There are other ways to express it. Alternatively, just blow my nose, hang on a second. Alternatively, you can use the real part. If I look at the real part of, what would it be? It would be e to the minus itx 5t divided by I of t, and this is all inside the real part. use the formula we had. The real part, I would have to add up. I have to add up the two conjugates, divide by 2. So take the first one will just be the number e minus it x 5t divided by it, and then I had 2. And then what? Then I'll have to add the conjugate of this one. Okay. So it's going to be something with a minus down here. There'll be a minus 2it down there. And then this thing changes signs again to itx phi of minus t. And you can see now this minus sign here, I can put it out there, and it's going to be exactly the same as what we had upstairs. This here will be equal to the imaginary part of e to the minus itx 5t divided by t. So there are different ways to write that integrand. We will use this formula here. Okay, so let's do that. So let's say that in, what is it that I want to do? I want to compute this limit here. I'll replace that integrand with what we had here. Okay, so I'll call in for this integral from 0 to n. Be e to the minus itx 5t minus e to the itx phi of minus t. Everything divided by 2it. dt. Okay, and it's this thing that I want to compute the limit of. This is the object I want to compute the limit of, and I want to prove that that limit is exactly this thing here. Okay, so let's try to work out. I have my phi t here. And my phi t here, I can insert the characteristic function. So let me write in the characteristic function. I'll get an integral from 0 to n. And then I'll have e to the minus itx divided by 2it. And then comes the characteristic function, integral over r e to the, say, iyt. Density was f of y dy. That was the first part. Minus. And then comes the second part. This is e to the itx divided by 2it. And then the characteristic function evaluated at minus t. So it's the same as what we have here. This is going to be a minus sign here. F of y dy integral over r. So that was the integrand. So now we put a dt out here at the end. Okay, so now let's try to combine everything into, you can see f, we can combine the two things, we can put the integrals next to each other. dt is on the out, dy is on the inner, like t is the variable that runs between 0 and n, y is the variable that runs over r. So combine, so we get an integral from 0 to n. So again, this here is my t variable. Integral over r, this is my y variable. Can you explain the last step? Yeah. Alice, let's try the last step again. Right, so here, what am I using? And I'm using that 5t. I'm using that 5t is as the integral over r of e. I'm using y here instead of x because x is already used for something else. So I write 5t here as e y t f of y dy. Right, that's how we go from the density to the characteristic function. And I'll use that phi of minus t is equal to the integral over r. And then instead of t, I'll have a minus I yt f of y dy. Right, so I'm doing nothing else than replacing phi of t and phi of t minus with the right-hand side that I have over here. I'm just taking these expressions on the right-hand side and plugging them into the formula. And I hope I did it right. So I have 2it downstairs, e to the minus itx upstairs. Here I'll have e to the itx upstairs, 2it downstairs. It looks good. So the only thing I did was I replaced the characteristic function. There are two of them. I replaced them. And now we're going to try to combine them because I can put the integrals like this here doesn't depend upon y. As a function of y, this is a constant, right? So he can go inside that integral. Same thing here as a function of y. This is a constant. He can go inside the integral. So I can put the two integrals next to each other. And then there's a common factor, namely f. I can put them outside parentheses. So let me try to do that on the next slide here. So what will we first have? We'll have this, like there's a 2it that's common, so we can put him downstairs. And then I'll have upstairs, I'll have e it, and then I'll have a y minus an x. That will be the first part, right? I'll have f of y here, and then I'll have my dt here. So that was the first part. Now the second part comes with a minus sign. And then I'll have e to the what? I would have e to the minus it, and then I'll have a y minus an x. Okay. So we have this mess in here. Let's try to work out. This is where that sine or x over x is going to ultimately come from. This is right here. And so let's recall Euler. Let's recall Euler's form. It says ei theta. This was what? Cosine theta plus I sine theta. And then of course, if I do it with a minus, e to the minus I theta, that's going to be the same thing, but with a minus theta in there. So since one of you asked if I drew cosine and sine correctly, let me just see if I get it right this time. So sine at 0 is 0. So this here is my sine. This is the odd function. Sine. So I can write that this is odd. Again, cosine at 0 is 1. So it looks like this. This is cosine. This is the even. So what do we see? If I take these two and I subtract them, because this is what we have enough here, right? I'm doing a subtraction here, and the only difference between them is this minus sign. So I'm doing a subtraction, e I theta minus e to the minus I theta. What would that give me? Well, I'll have to subtract away the two cosines. but cosine is even. So the cosines cancel. And then I'll have to take I, and then I'll have sine minus sine of minus theta, but sine is odd. So when I put a minus sign, it'll swap back up, and I'll get 2 here. Now we can simplify this expression up here. This means that my in, which is that stuff I have up here, this is the integral from 0 to n. And again, this is my t variable. This is my t variable. I have the integral over r. This is my y variable. Because of that little formula I had down here, I can greatly simplify what I have upstairs. The 2 i's will cancel. I'll just be stuck with something here that has a t. My theta will be this t y minus x. Then I have my f of y, and I have my dt. So again, the y integral is the inner one, the dt integral is the outer one. Then comes the time where we can do the swap. We'll use Lec4B. We'll switch them around. So now the y integral is going to come outside. So this here is my y variable. 0 to n. This is my t variable. So the dt comes inside. Y doesn't have anything to do with t. So I need to integrate this object here with respect to t. Sine t y minus x divided by t dt f of y dy. That's where we see the thing that we've been working on in the beginning of the class. So from the beginning of today's lecture, we know from earlier, we know that the limit as n goes to infinity of that integral, the inner integral of sine t divided by t and dt, we know that this thing is equal to pi over 2. So if I take a theta, if I take a positive theta, and I would look at the integral from 0 to infinity, understood in this sense, with sine theta t divided by t, what I would do is I would do a substitution. Right, I'll substitute here with s equals theta t. So I get that ds is equal to theta dt. And then when t is equal to 0, s is equal to 0, because theta is positive, I keep the plus infinity up here. And then I'll have sine of s. And then downstairs, instead of t, I would have s divided by theta. And instead of dt, I would have ds divided by theta. Right, so you see the thetas cancel out. I'll have an integral from 0 to infinity of sine sos ds, and this was exactly my pi over 2. That was when theta was positive. There'll be a similar formula when theta is negative. And you see the difference is going to be, like, that substitution here still works. The only difference is going to be that when when t is equal to plus infinity, s is going to be equal to minus infinity. So we're going to integrate from 0 to minus infinity, so that's going to be a minus sign change. We're going to get that the integral from 0 to infinity of sine theta over t, this is going to be minus pi over 2. So we have these possibilities, and of course if theta is equal to 0, you're just going to get 0. So we can combine into the integral from 0 to t, 0 to infinity. 0 to infinity of sine theta over t dt. We can write this here as sign of pi over 2, where that function sign of theta, this is what is 1 if theta is positive, it's 0 if theta is 0, and is equal to minus 1 when theta is negative. And again, all these integrals here that we're seeing, the all improper Riemann integrals. Right, so this is what we've been working so hard for. This is this pi over 2 here. And a little extension of this pi over 2 to allow for a parameter theta in here will allow us to generalize it. So we get this, depending on the sign of this theta, you're going to get pi over 2 or minus pi over 2. Okay, so now if we go back here, if I work on my inner integral and I pass n to infinity, so this here will allow us to say that if I look at the limit as n goes to infinity of that integral from 0 to n of sine, and so here I have t y minus x divided by t dt, what would that become? Well, that would be, using that notation up here, that would be sine. And then what matters is the sine of y minus x. And then it'll be pi over 2. That's the thing that's sitting inside here. Okay, we're interested in the limit of these INs and seeing what we get. Okay, so let's try to do that one. This is the final step. The limit as n goes to infinity of these INs, that would be the limit as n goes to infinity, integral over r, integral from 0 to n. So again, this here is my y variable, this here is my t variable, of that sine t y minus x divided by t dt f of y dy. If we could pull that limit inside, okay, so if we switch here, and we're ultimately going to see this using dominated convergence. So this here is just going to be C below. For now, we'll just move that limit inside, the integral over r here. So this is again my y variable. Pull the limit in here, and then I'll have an integral from 0 to n, and here I'll have my t. sine t y minus x divided by t dt f of y dy. All right, so let's take the limit, and let's say for now that we can interchange the first integral with the limit operation. And then we can use what we just had. We can use that limit, what we have inside here is this sine sign y minus x divided by pi over 2 times pi over 2. So that would become integral over r. Now this guy here is going to disappear. This is going to become sign of y minus x pi over 2 pi over 2 f of y dy. And now it will be natural to split that outer integral depending on how y and x relate. So if I do pi over 2, and then I'll integrate from minus infinity to say x of sine y minus x f of y dy. And then I'll do the same thing from x to infinity. Sign y minus x f of y dy. This will make it a little bit easier because when so here x is positive, so x is here, y runs between, so in this integral here, I'll have that y is less than x. So that means that y minus x is negative. This one over here, you get the opposite. Here, y is bigger than x. So y minus x is positive. Okay, so we get pi over 2. And here we're going to get minus an integral from minus infinity to x of f of y dy, because that integral now is -1. Y minus x is negative. This one over here is the opposite. I get a plus, an integral from x to infinity of f of y dy. Now it's finally starting to look better. It's finally starting to look better because I'm integrating the density up to x. This will give me pi over 2 times, this is minus f of x, plus, here I'll get f of infinity, that's a 1, minus f of x. So this here will be pi over 2 minus pi f of x. And this is what we were hoping we would get. That was our goal. So the proof is complete now, up to using dominated convergence, right? So we need to pull that limit from out here in there. So before I take you through the dominated convergence part, are there questions on what we've done so far? So the only part that's missing is I need to justify that I can pull this limit inside. And right, so the challenge there is to use dominated convergence. Let's see if we can use dominated convergence. So to use dominated convergence, let's write use dominated convergence. We write, so we have this integral. Bring it down here. How does it look like? We have an f. We have an f, and then we have a function here of n. So let's write this integral over r, and then we write this here as okay, call them for fn of y. I shouldn't call them f. This is also called f. Let me call them something else. Call them k. Kn of y, f of y. And so what is Kn of y? It's those things we have inside here. Sine t y minus x divided by t dt. Right, so what we need is we need a g such that if I take the absolute value of Kn, we're going to be bounded by dy, and when I plug it in, I'll be integrable. So instead of Kn, I'll write g of y, f of y, dy. This is going to be finite. So can I find some g that will do this trick? We need to look at how bad this k can be here. And let's have a look at it. So there's a y here. If I could get rid of the y, I would be able to use a constant. So let me try to write out what this. Can we get rid of the y? If we look at an integral from 0 to n, sine t y minus x over t. We'll do that substitution we had before. We'll do the substitution that says set s equal to ty minus x. And then I'll get that ds is equal to y minus x dt. And when t is equal to 0, this is equal to 0. When t is equal to n, I'll get n y minus x up here. And I'll have sine, and then this will be s divided by t would be s divided by y minus x. dt would be ds y minus x. So again, they cancel out as before. This is equal to the integral from 0 to n y minus x sine s over s and ds. And so what this shows is that if I could get rid of the y, I could use a constant for g. Okay, so what constant could I use? If I put g of y to be the maximum over that top parameter here, the maximum over a in r of that integral from 0 to a of sine s over s ds, I could pick this one. This one here is finite because the integral from 0 to infinity of sine, this is equal to pi over 2. If I looked at the integral from 0 to minus infinity of sine, then this would be equal to minus pi over 2. So when I take absolute value, I have these two endpoints, and in between you have continuity. So this is finite, and it's independent. This is a constant. It doesn't depend on y. And so if I take a constant here, I'll use it f as a density. I'm going to be fine. So that's the last part of the proof of the inversion theorem. The other, so that I understand this is a bit long. It's also a bit involved, but because we're going to be using this result quite a bit in the next lecture, and we're going to be using it in homework number 3. I wanted to show you guys where that formula is coming from. So this here is the inversion theorem, and it's stated under the assumption that f has a density. And let me just show you. How it would look like. We just show you how it would look like in case there's no density. So there is a version of this theorem when there's no density. So this here is if you take a PhD level or an advanced undergraduate course in probability, this is probably an introduction. At the PhD level, this is how it's used at Rutgers. If you take the first PhD course in probability, this is the material you'll be using. And if you go, so we're looking at characteristic functions, and the theorem you're using here is this inversion theorem 16.7, and if you flip over there, you will see here he is having a random variable that has an arbitrary distribution mu, and there's no density function. So he's going to pick up when you compute this integral that this is the one we've been working on. He'll pick up masses at potentially these endpoints. So I skipped, I didn't do that. I looked at the simpler case without these. And then he has the general formula down here under the assumption that you're integrable. So I want to derive this formula too, how to use the one we have up here to get the one we have down here. But if you ever are in the need of using this theorem here, when you have mass at specific points, then there is such an extension, and it's possible to do the proof that we just did, taking into account these points where there might be mass, right? With a density function, we know that we do not have mass at specific points. So let me do the corollary. We are at page 17. So we want to see how do we go from this formula. How do we go from this formula to this this corollary, and in particular, where does this assumption of integrability, where is that needed in the corollary? Let me see if I can get it to work. So proof of, so let me just restate the corollary. So the corollary is that if phi is integrable, well then you can recover the density simply by integrating 1 over, so there's this coefficient that you have to carry around, and then you put a minus sign, and then phi of t here. So you get the density back simply by computing integral of the characteristic function. And the proof is not bad. So you write f of x of that form that we had, 1/2 minus 1 over 2 pi bring it up here, right? So we write that formula. Minus 1 over pi, and then it was this integral. But instead of this I, this imaginary part with respect to time, let's plug in these alternative ways of writing it. Let's plug in, say, this form we have here. This would be minus e to the minus itx 5t. Need some more space here. Minus, then it was itx phi of minus t, everything divided by 2it dt. Okay, so we can break it up. 1/2 minus, I can pull the 2 outside, 1 over 2 pi. And then I can integrate from 0 to infinity, e to the minus itx 5t divided by 2i. 2i was already outside, so it's just it. And I have a minus and a minus, so this becomes a plus. 1 over 2 pi. Integral from 0 to infinity. And then I can do, let me just write out 2 steps, itx phi of minus t divided by it dt. And here I could do a substitution. Here I could do a substitution. I want to get this minus sign up here again, so I could do a substitution here that says s is equal to minus t. That substitution in the last integral. There's a substitution here that s is equal to minus t. Then this would become 0 minus infinity e to the minus isx. It will become phi of minus t will become plus, so this is s. ds, this would be minus ds divided by minus is. So lots of sign changes here. These two here will cancel out. There's a minus up here. I'll swap the order, put the minus sign out in front. And then you see we have exactly the one we have over here, but now the integral is running. The integral is running from minus infinity to plus infinity. And we end up with 1/2 minus 1 over 2 pi integral over r of e to the minus itx 5t divided by it dt. I combine these two guys in together. I have an integral here from minus infinity to 0 with a minus sign, so I get a minus sign there. It combines with these two, and I get an integral over r instead. So that's pretty close. And you can see if we just naively take a derivative inside, we'll get that f prime of x f prime of x would be, well, it'll be minus 1 over 2 pi. And then you have the derivative with respect to x of that integral. And you see, if you just naively move that derivative inside, you'll get, what do you get? You get 1 over 2 pi. Move the derivative inside, you're going to get an integral over r. Take a derivative with respect to x, you're going to get negative, so the negative signs will cancel. It will come down, it'll cancel out down here, and you'll get e to the minus itx 5t dt, which is exactly the formula that you want. The derivative of the distribution function, this is going to give me the density, and it has this form here. The problem is that you have this derivative that you have put inside without justifying it. So again, it goes through dominated convergence to make this rigorous, to make this possible. We use dominated convergence. We just recall what the derivative is, right? So we pick an h small. So f of x plus h minus f of x, that's the thing that's going to become a derivative when you take h to 0. We use the formula that we derived here, this guy. So this is going to be minus 1 over 2 pi. Then the first integral, e to the minus I, instead of x, you're going to have x plus h divided by it dt, and then minus f of x. So that'll be minus minus, that'll be a plus 1 over 2 pi integral over r, and then you have e to the minus itx f. There's a phi missing, right? There's a phi that should be there. Phi of t divided by it. Okay, we can combine these expressions. This is 1 over 2 pi. Combine these two expressions, this will be 1 over 2 pi. And then you will have an integral over r. And then let's put e minus itx outside, 5t dt. And then inside here we will have, there'll be a 1 from this one, minus, and then what we have from here will be e to the ith, and then we will divide by it times h. So we're missing an h here. And then the question is, can I use dominated convergence? What I need is, we need a g of t, such that, well, 1, you need it such that when I take the absolute value of 1 minus eith divided by th, that this is bounded by my g of t. The second property you need is that when I integrate g together with phi, I'm finite. So we need to know, how bad can this thing here get? How bad can this quantity here get? And it's very similar to what we had before. We can use g to be 1. And then 2 follows because phi was assumed integral. So that's the proof. We will not be able, we'll still be able to do the first one without that assumption, but we will not be able to get the second part to work without this assumption that phi is integral. So this was a lot. I get that this is a lot to take in, but we have now established a general formula, and then we established this specific formula for the relationship between the density and the characteristic function when the characteristic function is integrable. And what I want to do in the last 15-20 minutes is just to first do a sanity check, and then second to show you that this formula can be turned around and actually be used for as a computational tool. So the first sanity check is, let's just revisit the let's just make sure that all this stuff here makes sense in the case of the Gaussian. So that's the sanity check, and then we'll do an application that is not trivial. So the first one, this is the normal. This is my sanity check. Like the normal says that my density is 1 over root 2 pi e to the is minus 1/2 x squared. Right, and we know at this point that the characteristic function, we looked at it last time, the characteristic function is e to the minus 1/2 t squared. This one here is the density, right? And this here is the characteristic function. And we looked at that last time. So, so we know that this characteristic function here, this is going to be integrable. So because the integral of phi over r is finite, because this is integrable, we must have, and this is by the corollary, we must have that f of x can be written as 1 over 2 pi integral over r e to the minus I tx phi of t dt. So should we do a sanity check? Is that really true? Well, if you plug in what f is on the left-hand side, I'll get 1 over root 2 pi e to the minus 1/2 x squared. That's my left-hand side. So is it really true that this is equal to 1 over 2 pi integral over r e to the minus I tx? Phi was this Gauss function up there, e to the minus 1/2 t squared dt. Is that really true? Well, yeah, this is the same thing as asking that e to the minus 1/2 x squared, is that really equal to 1 over root 2 pi integral over r? I'm just moving the constant to the other side, and then I perform a substitution, namely s is minus t. I'll perform a substitution, then I'll get e to the isx e to the minus 1/2 s squared ds. And this is true because what we find here, this is exactly the characteristic function for our normal. Right, this characteristic function up here, remember, this was equal to the integral over r of e to the I tx f of x dx, and that's exactly what we find down here. But instead of evaluating it, like the Fourier variable here is t, the Fourier variable down here is x. So you just have to switch the variables, and this one here is, this is indeed true. It is true because phi of t was equal to that integral e to the I tx f of x dx. you simply substitute out t and x, you flip their roles. So what we have been doing for the normal, it really works. It's consistent with this more general result. Then I was thinking, like, okay, it's hardly convincing that we should spend a full lecture going over an example that we already know how to do. So I wanted to do something that was more difficult, something that was more tricky. And so let me show you another application that is new. So this here is also in, this one here is in homework too. If you look at f of x is not the normal now, it's like 1/2 e to the minus absolute value of x. So this is the Laplacian. This is the Laplace density. So here x is in R. So the first order of business is to compute f's characteristic function. So let's compute phi. Let's compute phi of t, the integral over R. There's 1/2 e to the minus absolute value of x e to the itx dx. Right, that's the characteristic function corresponding to this density. And this one here is not hard. And it's also in your homework, you work out what this one here is. There's a little bit of work there, but not very much. What comes out in the other end is this 1 over 1 plus t squared. It's not, this is not too bad, because what you're going to end up doing is just integrating exponential functions. So that's really not the new thing. The harder question is, the much harder question is, what happens if you consider Cauchy variables? It's for the Cauchy density. So recall what the Cauchy density is. This is g of x. This is 1 over pi, 1 over 1 plus t squared. X squared, right? It is, if you were to try to compute, so just try computing this integral 1 over pi 1 over 1 plus x squared e to the itx dx. Try computing this, just like what saves you up here is that you're computing products of exponentials, and it's easy to integrate the exponential function. Down here, it's a different ball game, because you have this exponential function, and then you have this 1 over 1 plus x squared. And normally when you see 1 over 1 plus x squared, you know this is hard, but you have this arctan substitution trick that's going to help you. Unfortunately, you also have an exponential function mixing up together. So this makes it hard. So let me show you how one can get this to work. Let's show you how one can make this to work. You look at this phi up here. So what we want to note is, note that phi of t being 1 over 1 plus t squared, note that this guy here is, this is integrable. Like again, what you need to do is integrate over r 1 over 1 plus t squared dt, and this is at this arc10 substitution that we had in the very beginning. But this was this arc10 substitution. This, I believe it comes out to pi. This is this arc10 substitution. So because this is integrable, I can relate phi and f in the Laplace case with each other using that corollary. So if I look at the left-hand side, this is 1 over 2 e to the minus x absolute value. That was the density. I can get that out by integrating, and then the characteristic function, that was 1 over 1 plus t squared, that was this guy, times 1 over pi, 2 pi, and then e to the minus itx dt. Because the Laplace characteristic function is integrable, I can get the Laplace density by integrating out into this characteristic function. So what does it have to do for the Cauchy? But you can see the Cauchy, it's almost there. It's almost there, right? To get the Cauchy, like I have to compute this integral, but look at what I have. It's almost there, right? What is missing is there's a 2, but other than that, and then there's a minus sign, but the minus sign probably doesn't matter because I'm squaring down here. And so we get almost for free. So we get almost for free. So the Cauchy characteristic function I have to get rid of. I can cancel out the halves, then it's just e to the minus x in absolute value. This is e to the minus absolute value of t. So try to compute this on your own and prove that this here really is e to the minus absolute value of t. I'm claiming that that is not very easy. Indeed, the proof that I've seen of trying to do this directly, this is not easy. But if you know this inversion theorem result, you can link it up with a Laplace density, and you can get something like this fairly easy. Because you get this identity, you cancel out the halves, and then it's just a question of getting rid of this minus sign. You can do that by substituting t to be minus s. This thing changes sign, this one does not change sign, and then you're done. Other questions on this part? We have like 5 minutes left, and given that we're talking about this Cauchy distribution, I want to return to this this question we had last time. So, given that we're talking about the Cauchy, let us return to an issue from last time. The issue from last time was that if I took a joint characteristic function, so let's do what should I call them, u and v, ux plus iv y, if I can prove that the joint characteristic function factors into the marginals, and this is for any u and v, this is the same thing as saying that x is independent of y. Okay, very good. The question we had last time, is it okay? Is it enough to consider u equal to v? Here it says for any u and v in R, if you can establish that the joint characteristic function factors, you get independence. What about if I just look at it on the diagonal when u is exactly equal to v? Would that work? And now we have the characteristic function for the Cauchy, this guy. We can answer this here now and say no. And the way we do it is let x be Cauchy. Let x be Cauchy. So the characteristic function of x is exactly that guy up there. And define, so the other one is going to be y. So define y to be a constant times x. For a constant c that's positive. All right, so now x and y, they're not independent. So x is not independent of y. Because one is exactly a constant times the other. But what about this left-hand side when u is equal to v? However, if I look at the left-hand side, so I'll have e to the I, and then a u. U and v are now the same. So here I'll have x plus y. What would that be? Well, I'll use that y is just a constant times x. So this here would be e I u, and then I'll have 1 plus my c times x. And then I'll use that x has characteristic function. I'll use that x is Cauchy distributed. This here is equal to e to the minus, then take absolute value of 1 plus c. Plus c. There should be a u somewhere. There's a u. It's absolute value of u times 1 plus c. That means to take absolute value of what we have here. We know the c is positive, so 1 plus c is positive. Now, if we at the same time try to compute the product of the marginals, the ones we have up here, I'll have e I u x. Well, what would that be? That we know is minus absolute value of u. And the other one is I u y. Then we use again that y is equal to a constant times x. And then what we get is the constant is positive, so we will have e to the minus c absolute value of u. And now if you combine the last two, you'll see that the product of the marginal characteristic functions these two, this is a u, e, I, u, y, what would it be? This would be e to the absolute value, e to the negative c times the absolute value. And that would be exactly the same thing as the characteristic function, the joint characteristic function evaluated at diagonal. So this is the same thing as that left-hand side over here, u x plus y. So it factors on the diagonal, but you do not have independence. So I'll put in this example here because now we have the characteristic function for the Cauchy, and this here is an application of the Cauchy distribution. The homework is asking you to look at other issues related to the Cauchy, for example, that it doesn't have any moments. You can already see here that the characteristic function has a kink. Right, this one here is kinked. This is kinked at 0. Right, and we know, as we talked about previous lectures, that one could use the characteristic function to compute moments by computing derivatives at 0. But here there's no derivative at 0 because it's kinked at 0. So there are also problems related to the Cauchy distribution when it comes to computing moments, and these moments don't exist, and so on. But this is in the homework here today. I wanted to show you, first and foremost, how to use this inversion formula that we've proven to calculate the characteristic function corresponding to the Cauchy. And as you can see, it becomes like a one-line proof, but that's because we've done so much hard work in the proof of that inversion theorem. But then given that, we can actually use it to settle this open question from last time. And it is insufficient to just check this product structure on a diagonal. You need to check it everywhere. Otherwise, it doesn't work. Okay, I went 5 minutes over time today. Are there any questions or comments here before we call it quits?
Could you re-explain the part on the second to last slide with the note? So how you got the Cauchy characteristic function again?
Yeah. Yep. Do that one more time. So when you look at the Laplace, then you have density f of x to be 1/2 e to the minus absolute value of x, and you had characteristic function phi of t to be 1 over 1 plus t squared, right? And because this is integrable, so because the integral of absolute value of phi is finite, I think is equal to root 2 pi. No, it's equal to pi. Right, this is arctan substitution. Like, because this is finite, we have that the characteristic function can be inverted using that formula we proved. This would give you f of x, right? Because this is finite, we have this relationship, and then we can plug in now. Plug in what f of x is. This will be e to the minus absolute value of x, 1 over pi. I'll cut away the halves here. Integral over r, e to the minus I t x. Phi here was 1 over 1 plus t squared, tt. But this is all what you get out from the Laplace case. So now we switch to Cauchy. There the density is g of x. This is 1 over pi 1 over 1 plus x squared. But you don't know what the characteristic function is. The characteristic function would be e of I tx, g of x dx, but you don't know what that is. But you can see it's very close. It's very close, like it's 1 over pi, and then instead of x here, you will have a t. So if you write this here as a substitution when s is equal to minus t, you'll get 1 over pi integral over r e, and then you get rid of the minus sign. So this is I, instead of t, is now s. And you'll have 1 over 1 plus s squared ds. So you can see you're interested in what is that, but this is exactly what you have up here. Because g of x is 1 over pi, 1 over 1 plus x squared. It's just the roles of s and x are swapped. But of course, nothing that prevents you from, instead of integrating with respect to x here, you can integrate with respect to any other variable, right? It's just a dummy. So you can put here an s if you want. And now you're much closer, right? So t here plays the role of x, and s is the same. So you get that this is equal to e to the minus, and then the role of t here is x. Okay, so you get absolute value of t. Yep. Other questions before we call it quits? Okay, then office hours with the TA tonight and tomorrow night, and then the office hours with me tomorrow morning at 9 o'clock, and the homework is due tomorrow night online. So if there are no more questions or comments, if I don't see you tomorrow, have a good weekend. Otherwise, I'll see you next Thursday.